In this video, we are going to review hydrohalogenation reactions of alkenes and work through several practice questions. As we go through these examples, we will focus on three important ideas: Markovnikov rule, carbocation stability, and carbocation rearrangements. These concepts will help us predict the major product when an alkene reacts with hydrogen halide such as HCl or HBr. Let's begin with a quick review of hydrohalogenation. Hydrohalogenation is a reaction in which a hydrogen halide such as HCl or HBr is added across the carbon-carbon double bond of an alkene. As you can see in this example, the pi bond disappears and two new sigma bonds are formed. One of the alkene carbons receives a hydrogen while the other carbon receives the halogen. So the overall result of hydrohalogenation is the conversion of an alkene into an alkyl halide. The important question is, when the two alkene carbons are different, which carbon receives the hydrogen and which carbon receives the halogen? That is where Markovnikov rule and carbocation stability becomes important. Hydrohalogenation is an electrophilic addition reaction, and it generally occurs in two steps. In the first step, the electron-rich pi bond of an alkene reacts with the hydrogen in the HBr. The pi electrons form a new carbon-hydrogen bond, while the hydrogen-bromine bond breaks and the bonding electrons move onto bromine. This produces carbocation intermediate and bromide ion. Notice that this first step is labeled as the slower step. Formation of carbocation is therefore very important in determining the reaction rate and the major product. In the second step, the bromide ion acts as the nucleophile and attacks the positively charged carbocation. This step is relatively fast and produces the alkyl bromide. So remember, electrophile first, carbocation intermediate second, and then the nucleophilic attack. When hydrohalogenation occurs with an unsymmetrical alkene, there are potentially two different ways that the hydrogen and the halogen could add. However, one constitutional product is usually favored. This is called regioselectivity. For hydrohalogenation, we generally follow Markovnikov rule. A useful way to remember this rule is that the electrophile, in this case hydrogen, adds to the sp2 carbon that already has the greater number of hydrogens. For example, when 2-methyl propene reacts with HCl, hydrogen adds to the terminal CH2 carbon. This places the carbocation on the most substituted carbon. That carbocation is more stable and the chloride subsequently attacks the carbon. Therefore, 2-chloro-2-methylpropane is the major product rather than 1-chloro-2-methylpropane. So the Markovnikov orientation is ultimately explained by carbocation stability. Now let's connect carbocation stability with the reaction rate. Remember that the slow step of the electrophilic addition is the step in which the carbocation is formed. Therefore, the stability of the carbocation intermediate has an important effect on the reaction. In general, a pathway that produces more stable carbocation is energetically more favorable than a pathway that produces less stable carbocation. As a result, formation of the more stable carbocation occurs more readily. This is also why the carbocation stability is so important when deciding which orientation of addition will give the major product. So, whenever you try to analyze an electrophilic addition reaction, one of the first questions you should ask is, which possible pathway produces the more stable carbocation? Before solving more reactions, let's review the relative stability of carbocations. According to the trend shown here, benzylic and allylic carbocations are specially stable because their positive charge can be stabilized through resonance. Among the ordinary alkyl carbocations, the order is tertiary is more stable than secondary, and then the primary, and then the methyl. Vinyl and aryl carbocations are shown the least stable end of this trend. For the reactions we are working with, the most important comparison will usually be between tertiary, secondary, and primary. So to keep the basic trend in mind, tertiary is greater than secondary, which is greater than primary. We will use this stability trend both to apply in Markovnikov rule and to determine whether a carbocation will rearrange. Another important feature of carbocation reactions is that carbocations sometimes rearrange. A rearrangement occurs when atoms or groups move along with their bonding electrons in a way that produces a more stable carbocation. Two common rearrangements that we need to recognize are the 1,2-hydride shift and 1,2-methyl shift. The term 1,2 means that the hydrogen or methyl group moves from a carbon directly adjacent to the positively charged carbon. The key point is that rearrangement is favorable when it converts a least stable carbocation into a more stable one. Let's look at each type separately. Now we have an example of a 1,2-hydride shift. The starting alkene is 3-methyl-1-butene and it is going to react with HCl. First, the double bond is protonated according to the Markovnikov rule. Hydrogen adds to the terminal carbon, leaving the positive charge on the neighboring carbon. This initially gives a secondary carbocation. Now we need to examine the carbons adjacent to this carbocation. The neighboring carbon contains a hydrogen that can migrate. That hydrogen moves together with the pair of electrons from its carbon-hydrogen bond to the carbocation center. This is a hydride shift. Notice what is going to happen to the positive charge. It moves to the carbon from which the hydride is originated. Chloride then attacks and it will form the product. Without the rearrangement, we would obtain 2-chloro-3-methylbutane. But because formation of the tertiary carbocation is favorable, the rearrangement product is favored. So we will see 2-chloro-2-methylbutane as the major product. Now let's look at a 1,2-methyl shift. In this example, 3,3-dimethyl-1-butene is going to react with HCl. As before, the protonation of the double bond initially produces a secondary carbocation. We then examine the adjacent carbon to see whether rearrangements are possible. In this case, the neighboring carbon does not have a hydrogen available, but instead it has 3 methyl groups. One methyl group can migrate from the adjacent carbon to the carbocation center, carrying the electrons from the carbon-carbon bond with it. When this methyl shift occurs, the positive charge moves to the carbon that lost the methyl group. The important result is that the original secondary carbocation is now converted to a tertiary carbocation. Chloride then comes and attack to form the product. So remember, if a hydride shift is not possible, check whether there is an alkyl group, commonly a methyl group, can shift to produce a more stable carbocation. However, we shall not assume that every carbocation will rearrange. A rearrangement generally occurs only when it produces a more stable carbocation. In this example, the reaction with HBr initially produces a secondary carbocation. But if that shift simply converts one secondary carbocation into another secondary carbocation, then there is no significant improvement in the carbocation stability. Therefore, the rearrangement is not favored. Instead, bromide attacks the original carbocation directly. This gives us an important problem-solving rule. Whenever a carbocation forms, check the neighboring carbons for a possible hydride or alkyl shift. But do not perform a rearrangement automatically. Ask whether the proposed rearrangement actually produces a more stable carbocation. If it does not, the carbocation will typically remain where it is. Now, let's apply these ideas to a practice problem. Here we have a methyl substituted cyclohexene reacting with HBr. Your task is to predict the major product. Before continuing, I recommend pausing the video and working through the reaction yourself. Remember the steps. First, recognize the reaction type. Second, determine where the hydrogen should add. Third, draw the carbocation intermediate and determine its stability. Fourth, check whether the carbocation can rearrange. And finally, allow bromide to attack the carbocation. Pause the video here and try to predict the product before continuing. Let's begin working through the reaction. The reagent is HBr, so this is a hydrohalogenation reaction. Because no peroxide conditions are indicated, we use normal Markovnikov pathway. Look carefully at the two carbons of the double bond. If we label these alkene carbons, let's label them as A and B. Carbon number B has a methyl substituent, making it more substituted. The other alkene carbon, carbon number A, has more hydrogens. Therefore, H plus from the HBr, which is going to serve as the electrophile, is going to add to carbon number A. So now let's see how we can draw the product. When we try to predict the product, first we draw the rest of the molecule as it is. So we need to draw the rest of the molecule as it is. And then H plus should add to the sp2 carbon where it is less substituted. And then we need to see what kind of carbocation we are going to produce. Here in this case, we are producing a tertiary carbocation. A tertiary carbocation is a stable carbocation, so no rearrangements are necessary. So now, bromide ion will come and attack this carbocation and we will get the product. So let me draw the product. We draw the skeletal structure or the rest of the molecule as it is. H plus will be adding to the place where we have less substituted sp2 carbon, and then the bromide will be added in here. So this is our final product. Here is my major product. Let's summarize why this product forms. HBr adds to the alkene through Markovnikov addition. First, the pi bond is protonated so that the hydrogen is going to add to the less substituted alkene carbon, and then it will place the positive charge on the carbon bearing the methyl group. The carbocation is tertiary and therefore more stable, and no rearrangements are necessary. So we do not expect a hydride shift or a methyl shift. So the key reasoning in here is that Markovnikov protonation, and it will form the tertiary carbocation, no rearrangements, and finally our bromide ion will come and attack the carbocation and it will lead to the product. Before answering the next questions, let's quickly review our carbocation stability trend. Resonance stabilized carbocations such as benzylic and allylic carbocations are relatively stable because of the resonance stabilization. For simple alkyl carbocations, remember the trend. Tertiary carbocations are more stable than secondary, and then they are more stable than primary carbocations and then methyl carbocations. The number of carbon groups attached to the positively charged carbon is therefore very important. As we look at the next structures, identify exactly where the positive charge is located and then count how many carbon groups are directly attached to that carbon. This will allow us to classify each carbocation and then we can use it to predict its stability. Now consider these 4 carbocations labeled A through D. Before I give you the answer, pause the video and classify each positively charged carbon as primary, secondary or tertiary. If you finish figuring that out, let's compare them. In structure A, the positive charge is located on the ring carbon right here. And it is having a methyl substituent and a ring carbon and also connected to another ring carbon. So basically, in structure A, we are having a tertiary carbocation. If we try to understand what is happening in structure B, we see the positive charge in here. And that positive charge is connected to 2 R groups or connected to 2 carbon groups, making the carbocation in structure B as a secondary carbocation. In structure C, we have the positive charge in here. That positive charge bearing carbon is connected to one other carbon, one R group. So, the carbocation in structure C is a primary carbocation. When we look at structure D, we see the positive charge in here. The positive charge bearing carbon is connected to 2 other carbons. So, in structure D, the carbocation is a secondary carbocation. So now we have a tertiary carbocation, a primary carbocation and 2 of the secondary carbocations. So which one is more stable among the carbocations that we have in here? Definitely, the most stable carbocation is A because it is a tertiary carbocation. For our final question, determine which of these carbocation does not rearrange. The best approach is to look at each carbocation and ask whether a 1,2-hydride shift or 1,2-alkyl shift could produce a more stable carbocation. Let's start with A. Structure A is already having a tertiary carbocation. A simple neighboring shift would not produce a more stable carbocation. Therefore, there's no strong driving force for rearrangement. So the carbocation in A is not going to rearrange. Now let's look at structure B. In B, we have a secondary carbocation. On the neighboring carbon here, we have a hydrogen. That means there's a possibility to do the 1,2-hydride shift. Let's see by doing that whether we can improve the carbocation stability. So, I'm trying to draw the structure in here. The rest of the molecule won't change. I'm only exchanging the positive charge with the hydrogen atom on the neighboring carbon. If I do that, my positive charge will move onto this carbon and the hydrogen will move in here. So now I initially had a secondary carbocation. Now I'm going to have a tertiary carbocation. Tertiary carbocations are stable than secondary carbocations. So by doing the 1,2-hydride shift, I can improve the carbocation stability in structure B. So B is going to rearrange. If we look at structure C, I have a primary carbocation. On the neighboring carbon, I have a hydrogen. And let's see whether we can do 1,2-hydride shift. If I do that, my positive charge will move here. So initially I had a primary carbocation. Now if I do the 1,2-hydride shift, I can produce a tertiary carbocation. Tertiary carbocations are stable than primary carbocations. So the carbocation in C is going to rearrange. If I look at structure D, I have a secondary carbocation. And on the neighboring carbon, I have a hydrogen. So I can propose 1,2-hydride shift. Let's see by doing that whether we can improve the carbocation stability. Yes, I can do that. That means initially I had a secondary carbocation. By doing the hydride shift, 1,2 hydride shift, I can improve it to a tertiary carbocation. So, D is going to rearrange. So, what you need to remember in here, the overall lesson is simple. Always compare the stability of the carbocation before and after the proposed shift. Rearrangement is favored only when it leads to a more stable carbocation.